So these new set of notes are going to talk about what we call sampling distributions, all right? And in a sampling distribution, what it is it's basically looking at every one of your samples that you can take from a population, the different statistics you can get. And what I mean by that, let me give you a quick example, is let's say we're interested in the average height of people at a school. Well, we could go into classrooms and take samples out of each one. Let's say have the same size, of size 10 from each class, and look at their average height. More than likely, most of those heights are going to be around the same values, but they're not all going to be the same numbers. So in a sampling distribution, we know what the actual values are, and we know the distribution of those. We have all of the different samples you could take. So a sampling distribution is the probability distribution of a sample statistic. And remember, a statistic is from the sample. A statistic is an estimate. It's an estimate that comes from the sample. And we use it to estimate what we call our parameter. And the parameter is the true value of the population. So there, like I was saying earlier, there is an average height, a true average height, but we always use the sample to try to estimate that. And what we're trying to talk about now is we're going to develop this thing we call the central limit theorem, where what's going to happen is most of your values are going to fall around an average height. So most of your samples will have a sample value that's around average height. But some of those values, though, are going to be from very far away from it, and some of them are going to be very close to it. So what ends up happening is we develop this thing called the central limit theorem. And the central limit theorem describes the relationship between the sampling distribution, so all possible sample statistics of the sample means. And we're interested in the sample mean, which we call X bar, and the population mean, which we call mu, that the samples are taken from. And if we have samples of size n, where this is the big rule, and this is what we call our sufficiently large rule, where n is greater than or equal to 30. So we need the samples that we take to be greater than or equal to 30. We need to take at least 30 samples, is the saying. And the other thing is, regardless of shape, when we talk about shape, remember our shapes are left, right, and symmetric. So regardless if the distribution is left, right, or symmetric, it doesn't matter. What this is saying now is that if we look at the sample means, which are the X bars that come from that population mu, the X bars will all be approximately normal. And this is a nice fact. Because we know how to calculate normal probabilities, and because we know how to do normal probabilities using normal CDF, we can actually calculate probabilities using the central limit theorem. So here's what the central limit theorem actually says, and here's why we're going to use it. If n is greater than 30 and we are looking at X bar, the sample mean, the sampling distribution first is approximately normal, which we've already stated. It is approximately normal. It is not fully normal, but it is very close, or it is sufficiently normal for us. And the mean of the distribution is centered at mu of x. So what that really means is that if you look at all X bars, and if we put all those X bars, all those different means that we got on the chart, we would see that they would follow a normal distribution. And that normal distribution will be centered at whatever the population distribution is. That's what that is saying. So what is also saying is that the sample mean is a very good estimate, or that X bar itself is a very good estimate of the sample, of the actual population. And the standard deviation, which is what we call our standard error now, it's called the standard error. So we used to talk about the standard deviation as sigma x. That was standard deviation. But now when we do this, we're looking at the standard deviation of sigma x bar. And this is equal to the new standard deviation for us. And our new standard deviation, also known as the standard error, is the old standard deviation, sigma x, divided by the square root of n. So this is what makes it new. We're dividing by a square root. And then the last thing says, if the distribution from which the population is drawn is normal, if it's already normal, if we draw from a normal population, then we don't have to have that n greater than 30, that sufficiently large part met. And we can still use central limit theorem. So here are examples, and here's what we're going to do. For these particular problems, we're going to see if we can use central limit theorem first, And then we're going to find the mean and the standard error of the sampling distribution of the mean. So the first problem says cell phone bills for residents of a city have a mean of $47 and a standard deviation of 9. Random samples of 100 cell phone bills are randomly drawn from the population. Find the mean and standard deviation of the sample means sampling distribution. So I'm interested in the sample mean sampling distribution. That already tells me I'm talking about the mean of the X bars. And so what's going to happen is then, when I do this, I want to verify that n is bigger than 30 first. The magic number is 30. And I see that I have samples of 100 here. So I know my n equals 100. And so that means n is greater than or equal to 30. So what we say is by CLT, because n is greater than 30, the mean of the X bar, or the value of X bar, is approximately normal. And every normal distribution has two parameters, which are the mean and the standard deviation. Well, the mean of this is whatever the mean of the population is. So the mean of X bar is going to be the same thing as the mean of the population, which in this case is 47. So the mean of X bar is 47. And the standard deviation of X bar now is something that's new, because it's going to be called the standard error. So what we do is we take our standard deviation, which is 9 in this case, and we're going to divide it by the sample size. So we're going to take 9, and we're going to divide that by the square root of 100. And so now I get a new thing. This value right here is called the standard error. And that is going to be the only true difference. And what we're trying to do now is just identify these parameters. That's all we want to do for this problem. So we do the same thing down here on this problem as well. Assume the training heart rates of all 20-year-old athletes are normally distributed with the mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from the population, and the mean is determined for each. Find the mean and standard deviation of the sampling distribution. Again, we're looking at the mean and standard deviation of the sampling distribution of the sample mean. So the first thing I'm going to check for is n. I want to know what is the value of n, and they tell me that I have random samples of size 4. That's a problem because 4 is not bigger than 30. But the other thing that can go, if we look at this again, at this particular thing, it says, if the distribution from which the sample is drawn is normal, then we don't have to meet the large condition. So let's go back and read. And it tells us that assume the training heart rates of all 20-year-old athletes are normally distributed. So because they are normally distributed, what that means is that by CLT, X bar, we're talking about the sample means again, X bar is approximately normal with a mean of the population, with the mean from the population, which in this case, our mean is 135 beats. And a standard deviation of this number divided by the square root of the sample size. And this is the big thing that's different on this problem, is that we have a sample size that we're calculating now. And when you calculate with a sample size, you have to go and divide by the square root of it.